All right, guys, today is our last lesson for AP Calc is the slope fields. Uh, and what a slope field is a graphical representation of the solution to the differential equation. So as we say here, it is a pictorial of all, that's the key thing right here, of all possible solutions to the differential equation. Remember that the differential equation of like a first derivative here, thus there is the solution to the differential is the function f of x or y. Just like what we did the last one, we have to separate the variables and then integrate. So for this instance right here, find there's an infinite number of solutions to this differential equation. Show it. All right, so what we're going to do is we're going to separate the variables right here. So I'm going to multiply both sides by dx. So I end up with dy equaling x plus 3 dx. And then we are going to integrate both sides. Integrating both sides, we end up with y equaling x squared over 2 plus 3x plus c. Now, the reason why we say it's infinite number of solutions is because right here, there is no initial condition. C can be anything you want it to be. So this is why we have infinite many solution. This right here is called the general solution. This is the general solution of this particular problem of dy dx equaling x plus 3. It is a general solution. And it represents all the this is a quadratic, by the way. And it represents all quadratics. Why is it all quadratics? Because we don't know what that c is. That could be the derivative. All right. Excuse me. So this is what slope fields is. Sometimes when we give you the initial condition, we will figure out what this is, and then we have to draw that. So before we move on, let's talk about what the AP exam is asking you to do. It has 4 things to do with slope fields. 1, it would like you to sketch a slope field given a differential equation. So just like what we did up there, they gave us a differential equation and we had to sketch it, but we didn't do that yet. And again, another key word for differential equation is the dy dx. You know you got the derivative. 2, given a slope field, if they give us a slope field, draw a particular solution. Now, the key word here is particular. Up here was general. A particular solution is when we have the initial condition up there. 3, match a slope field to a given differential equation. So in this one, you need to match the drawing to the equation. So if they gave us this equation up here, dy dx equals x plus 3, you have to match its graph. We'll get to that. And finally, match a slope field to a solution. This was to the equation, and now this is to the solution of a differential. So we are going to do these 4 things. We're going to sketch. We given the slope field, draw the solution, match in both cases. All right, so let's start with number one. Sketch a slope field for a given differential equation. So we were talking about that problem, x plus 3. This one's a little bit different. It says dy dx equals to x minus 1. So in order to do this, by the way, when we sketch a slope field, the slope field should look like a collection of f primes of, I'm sorry, not f primes, of f of x, not f prime of x, okay? So the slopes, okay? So here, we know they gave us dy dx. We know this is a slope. This is another word for, this is another way to write slope. So, and they want us through the points. So let's do through all of these points. So I'm going to start with the leftmost, which is -2, 3. So at -2, 3, what is the slope? Well, plug in x to be -2. -2 minus 1, which equals -3. I know, so the slope here is a -3, so the slope must go down this way. And I'm going to keep on continuing for every single point. But I'm just going to go, I'm going to go across real quick. -1, 3. That gives me -1 minus 1, which is -2. As you see, this slope is not as steep as that one, so we might make it a little bit more flatter. At 0, 3, we get 0 minus 1. Again, less flat. At 1, 3, we end up with 1 minus 1. So now we have a 0 slope, so that's this line like this. And finally at 2, 3. 2 minus 1, which is 1, we know this is going up. As you see, no matter what, this only has one variable x, so I'm only looking at the x value, and I'm subtracting 1. So if you look at it, if I plug in 1, 1, 2, all of this is going to be a flat. These all give me zeros right here. If I plug in -2, all of these are going to be -3 slopes. So they're all going -3, -2, -1, even at 0. And these are going to give me positive 1s. As you can see here, just like by like a motion, it looks like going down like, and then up like that. All right. So same thing with the next problem, x minus y. Exactly the same thing. So again, I'm gonna start at -2, 3. If I, well, this one a little bit different. It has both x and y. The other one just only had an x, so that plays a big role. So just to double check, plug in -2, 3. I get -2 minus 3, which gives me a -5. So at this right here, it's a very steep slope. If I do -2, -2, because now it differs, I'm going to do going downwards. We end up with -2 minus, oh, I'm sorry, -2, 2, sorry. -2 minus 2, which is a -4. As you see, it's a little bit more flatter. -2, 1. More flatter, whoops. -2, 0. As you see, it's getting flatter and flatter and flatter, isn't it? So the only time that it's going to be 0 if x is the same as y. So at -2, -2, I know I'm going to end up with a 0. -1, I'm going to end up with a 0. 0, 0, I'm going to end up with a 0. 1, 1, a 0. 2, 2, I'm ending with a 0. And this is going this way. Same thing right here. If x is bigger than y, if y is bigger than x, it's a negative slope. Y is bigger than x, so slope are going downwards. But here, -1 is bigger than -2, because that's the x, that's the y. That means this must be going up. So you can check -1 minus a -2 is a +1. So technically, you can see that here at this path, they're going up. And here it's going to go up further. That means it's bigger slope, and even a bigger slope right here. Here is going to be a more downward slopes. So x minus y. If you actually solve this, you get y equals to x, which is a straight line. As you see, kind of that's what it's hinting at. All right, so this is sketching a graph. Sketch a slope field to a given differential equation. All right, the second thing that we have to do is, given a slope field, so we're giving you the slope field, sketch a solution curve through the given point. All right, so first of all, this is the derivative. This is linear. So if the derivative is linear, then that means the solution should be going backwards. Let's say this is just x. If I take going backwards, the derivative is x. That means it came from an x squared. So power of 1 comes from power of 2. So the solution should look like parabola. And I'm saying it should look like. But they want me to go through the point 1, -1. So at 1, -1 is right here. See it? So I need to draw a parabola that goes through that point. So this must be my like vertex. And as you see here, look at the slopes. They're going down to 0, then they're going back up. Can you see? Now remember, this is a possibility. I can have one thinner, one wider, whatever, but it doesn't matter as long as it goes through that. So here is a possible solution to sketch a slope field, given a slope field, sketching the solution curve through that given point. Again, because we don't know what C is going to be, I don't know what this is going to be here, 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 anything that is above this -1, because we were going to go through that 1, -1. So step 2 is not, the second way is not that complicated. You just look at the point that they give you and, oh, okay. If it's a quadratic, you know it's a cubic, so that should be like an S. Even the slope fields will mimic that. All right. So the third thing that we are doing is matching. Match a slope field to a differential equation. Since the slope field represents all the particular solutions to this differential equation, the solution represents the antiderivative of the differential. So the slopes, the solution is the antiderivative. Then the slope field should take the shape of that antiderivative. Okay, so we have 10 graphs right here on this page. and we have 10 equations here. Okay, so let's separate these variables right now and figure this out. So let's do number one. We have dy equals sine x dx. Integrate both sides. Y is going to equal to a negative cosine x plus c. So the question becomes, do I know how negative cosine looks like? I know cosine looks like this. So negative cosine should be the reverse, like that. So which one of these, if you look at A, it looks like a parabola. Nope, that's not a cosine curve. This looks like, oh, do you see it? Nope. This looks like, you see how it's going down to 0? That looks like x to the third to me. This one, you see the wave? This one looks like this and like this. This looks like a parabola. These are all zeros here. So it goes up and down, so it looks like a negative. Let's see, this one. This one looks like a W, doesn't it? See it? This one. Down, up, and down. Oh, that kind of fits. So you might ask, why is this different than D? Well, J, if you look at J, it's just going straight lines. How is I different than D? Let's take a look at that. Here, it looks like it's like this. Do you see it? It looks like more of a sine curve. This, it goes up and down. So we're going to say number one matches I. Number two, dy equals to 2x plus 4. Integrating both sides, y is equal to x squared plus 4x plus c. So we know this is a parabola. We know it opens up. Okay, so I is gone. So we need one parabola that opens up. Let's see, what else we know? Can we find the vertex? Of course, the vertex here would be minus b over 2a. So minus 4 over 2, which is negative 2. So the vertex is at negative 2. So I'm looking at a parabola that somewhere the vertex is at negative 2. Could be any one of those. So here we go. As you see here, this looks like a negative 2 right here. And it opens up, so that's a possibility. No, 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 no. This is it is an x squared, but the vertex is not at negative 2. No, no, and no. So the only one that fits that is A. So 2 is A. And number 3, dy dx is e to the x. So dy is e to the x dx. So y is equal to e to the x plus c when you integrate both. Well, we should know e to the x, that looks like that. Oh, we've seen that. That looks like b. See it? So that does it. dy dx equals to 2. So dy is 2 dx. Integrating, y is equal to 2x plus c. So this is linear. Okay. It's a straight line, linear, slope of 2. Well, that's not linear. That's not linear. E is not linear. That's not linear. Not linear. The only one that's linear is J. All right. So I hope you understand what's going on. I'm going to do the problems and just going to give you the letters, and then you can go back and check. So if I separate here, we get x cubed minus 3x dx. we get y equaling x to the fourth over 4 minus 3x squared over 2 plus c. X to the fourth is a W curve, kind of, and you should see that with the letter H. Number 6. Can I just jump in? This is going to be over here. So if I integrate, I get y. The integral of 2 cosine x is 2 sine x plus c. Okay. Oh, remember that's the curve. Remember we were talking about d. So h is gone. So d is the sine curve. See it? All right. 7. The integral of 4 minus 2x is 4x minus x squared plus c. This is a negative x squared. That's the one that opens downwards. And minus b over 2a, so that's minus 4 over 2 times negative 1. That would gives me a 2. So the vertex is at 2. So you can tell opening downwards and the vertex is at 2. That could be a solution right there. So that's G. Y equals x squared over 2 plus c. This is just 1/2 x squared. So its vertex is at 0, 0. Oh, okay. So the one that's at 0, 0 that looks like a parabola is this. So here's a possible solution. So that's F. Next, y equals x cubed over 3 plus c. This is a cubic. Well, we saw that when we were describing this. That looks like this right here. So that's the letter C. Finally, by elimination, this has to be E. But here we have y equals negative natural log of x plus c. That's why the graph looks like that. All right. So I believe that is the third one. And finally, the fourth one is to match a slope field to a solution. So again, here we have these 10, and we need to match this slope field to these solutions. Okay, so remember, this is y, see it? Y is equal to x. Which one looks like y equals to x? Well, again, let's go through these. This looks like a parabola at 0. See it? That looks like a curve, like a sine curve. This is a linear. This looks like 1 over x, or maybe 1 over x squared. Curve could be sine or cosine. This looks like E. These are linear but horizontal. This looks like, oops, sorry, right here. Linear horizontal. This looks like an x cubed. I, it looks like we have something here, something's going on here. We'll talk about that. And this looks like we have just this side right here. It looks like that. All right, so let's talk about y equals to x. So that's a straight line from A through J. The only one that kind of fits there is C. Here's y equals to x. 2, y equals x squared. So I know that looks like this. Center's at 0, 0. If you really look at it, y equals x squared. Center could be 0, 0. Could be one of these. So it has to be A. See, these they give you the solution. We don't have to integrate like the last one. So these are the solutions. 3, y equals e to the x. Again, e to the x looks like this. So it's not b. That doesn't look like that. That looks like f. See it? So that's f. 1 over x squared. That's this one. So, oh, hold on. F is taken. I'm at 1 over x squared. Oh, that looks like d, doesn't it? See it? X cubed. X cubed looks like this. So that should, it's not b. Well, d's gone. It's not e. It's not g. It looks like this. See it? Possible x cubed. So it's h. Sine x. All right. We have a couple here. So in order for you to figure out what it is, what would be its derivative? What's dy dx? What's the derivative of sine? The derivative of sine is cosine x. So, and I know at 0, cosine of 0 is 1. I know at 0, comma 1. I know when x is 0, y is 1. So which one does that fit? Does that fit b at 0, comma 1, almost? Does it fit e? But see, E is like a, you see it? You see how E is going? It's going like this. This is going up and down. That's the sine curve right there. So it has to be B. Cosine x, well, we know that is going to be sine x, right? Its derivative. And cosine, this is what E is, isn't it? See how it starts at 1? Goes down like this. See it? If I do a particular solution, that's a cosine. This is what? A sine curve. So E square root of x. Well, we know square root looks like that. So it's either G, I, or J. That's straight. This is what that looks like. See it? So it's J. Y equals to 1. Y equals to 1 is a horizontal line. That kind of gives it away, doesn't it? So that has to be G. Y equals to 1. So finally, tangent x. Well, we know how the tangent should look like. It's from negative pi over 2 to pi over 2. Those are our asymptotes. And then it keeps on repeating. Oh, sorry, here you go. That's why you have your asymptote. See it right here and here? How this goes like this. It keeps on repeating. So this is I. Okay. So this is matching a slope field to a solution, which is a little bit easier because they gave us the solution. All right, let's do these two problems real quick. Shown below is the slope field for which the following differential equation, for which of the following differential equation? Okay, so here we go. You can see this either it opens up and then what? It opens down, doesn't it? So let's take a test. Let's test negative 1, 1. Test negative 1 and 1. What does that mean? Here, at negative 1, 1, right here. See it? I'm testing that. All right? We know that the slope at negative 1, 1 is 0. That's why I wanted to test it. All right? Let's test here. Is negative 1 times 1 0? Nope, that doesn't fit. Negative 1 times 1, which is negative 1, minus 1, right? Plug it in. Negative 1 times 1 minus 1. Negative 1 minus negative 1, that's not 0. Negative 1 plus 1, possibility, possibility. Negative 1 plus negative 1, no. Negative 1 plus 1, which is 0 to the third, which is still is 0. Nope. So the only one that works is that. Okay, so you might say, well, what about over here at negative 2? Let's just pick a different point right here. Pick that point. That looks like negative 2, negative 1. You know, if you plugged it in, you see that at negative 2, negative 1, it should give you a positive 1 slope. So if I plug it in here, I should end up with a positive. So let's see. Negative 2 times negative 1 plus negative 1 gives me a positive 1. Yes, see that slope right here is a positive slope, so that works out. So the answer to that is C. And then finally, this last one, consider the differential equation to answer the following questions. Sketch the slope field, sketch a solution that goes through 0, negative 1, find a particular solution. All right, so I'm going to separate the variables, y dy equals x dx. So we end up, when we integrate, y squared over 2 equals x squared over 2 plus c. Since I want the point 0, negative 1, x is 0, y is negative 1. So we end up with negative 1 squared over 2 is equal to c, which gives me c equaling to 1/2. So we end up with y squared over 2 equaling x squared over 2 plus 1/2. Now we need to solve, we have to solve for y. So multiplying both sides by 2, we end up with y squared equals x squared plus 1. So y equals the square root of x squared plus 1, that's plus and minus. Again, when x is 0, we want to be negative 1. So now we know we're looking for that negative square root. All right, so we're at 0, negative 1, which is right here. Okay. And as you see, here's my derivative again. dy dx is x over y. So when x is 0, all of these are zeros. These slopes right here are all zeros. Okay. So let's see what happens when, now remember, this is x over y. So let's check over here. This is negative 1, negative 2, and this is 3. So negative 2 over 3, negative 2 over 2, negative 2 over 1, right? Negative 2, so it's a bigger slope. Negative 2 over 0, can't have it. Oops, I don't know why you did that. This is wrong right here. I can't have 0, can't divide by 0. This one right here, and it should look like that. And these are going to go down like this and look like that. Those are zeros at 1. As you see, we are looking for this negative. So I know, let's just do this last one. Since the top would have been the positive, but we want the bottom. which is this. All right. So this ends the slope fields. Not that too difficult. It's just it's a pictorial way of finding the solutions. I will send you the homework for this in a second. All right. Bye.